Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about concept of jointly Gaussian random variables. So jointly Gaussian random variables concept, I am going to discuss about two random variables and capital N random variables. First, we are going to discuss about two random variables concept. If two random variables x1 and x2, capital X1 and capital X2 are the two random variables are said to be jointly Gaussian, then their joint probability density function is given by mathematically fx1 x2 of x1 comma x2 is equal. So this suffix x1 x2 are the two random variables x1 and x2, and this x1 and x2 are the values of the random variables. So the jointly probability density function is fx1 x2 of x1 comma x2 is equal 1 divided by 2 pi sigma x1 sigma x2 square root of 1 minus rho square into exponential of minus 1 by 2 into 1 minus rho square into x1 minus x1 bar whole square divided by sigma x1 square minus 2 rho x1 minus x1 bar into x2 minus x2 bar divided by sigma x1 sigma x2 plus x2 minus x2 bar whole square divided by sigma x2 square. Here x1 bar is the mean value of the random variable x1, that is also written as expectation of x1, and x2 bar is the mean value of the random variable x2, and it is also written as expectation of x2, and sigma x1 square is the variance of the random variable, variance of the first random variable, and the variance of the random variable x1 is expectation of x1 minus x1 bar whole square, and sigma x2 square is the variance of the second random variable, and it is expectation of x2 minus x2 bar whole square. And rho is the correlation coefficient between two random variables x1 and x2, and it is given by expectation of x1 minus x1 bar into x2 minus x2 bar divided by sigma x1 into sigma x2. So sigma x1 and sigma x2 are the standard deviation. The standard deviation is the square root of the variance of the random variable. The locus of the constant amplitude points gives an elliptical shape. This shape degenerates into a circle if sigma x1 is equal to sigma x2 and sigma x1 is equal to sigma x2, then the correlation coefficient rho is equal to 0. Correlation coefficient rho is equal to 0. So the maximum value of the density function is located at x1 bar comma x2 bar. That maximum value is two random variables. Maximum value is fx1 x2 of x1 comma x2 is equal 1 divided by 2 pi sigma x1 sigma x2 into square root of 1 minus rho square, and this is the equation of the two random variables two random variable Gaussian jointly Gaussian random variables. Jointly mean two random variables, Gaussian random variables, probability density function expression. And next we are going to discuss about n random variables Gaussian concept. So now here n random variables, consider capital N random variables x suffix n, where small n is equal to 1, 2, 3 and so on capital N. That capital N random variables are said to be jointly Gaussian if their joint probability density function is given by f x1, x2, x3 and so on xn is equal xn of x1 comma x2, x3 and so on xn is equal 1 divided by 2 pi whole to the power of n by 2 determinant of matrix C whole to the power of 1 by 2 into exponential of minus 1 by 2 into x minus m transpose into C inverse into x minus m. So this is the expression of the n random variables giant probability density expression, general expression. So now here in this equation, capital T is the transpose of the matrix X minus M. C inverse is the inverse matrix of the C, and X minus M is the matrix X minus M is the x1 minus m1, x2 minus m2, x3 minus m3, and so on, xn minus m1. So now here small m1, small m2, and so on, small mn are the mean values of the random variable. So that is m1 is equal to expectation of x1, m2 is equal to expectation of x2, m3 is equal to expectation of x3, m1 is equal to expectation of xn. The expectation of x1 is also denoted as x1 bar. Expectation of x2 is also written as x2 bar. Similarly, expectation of xn is also denoted as x suffix n bar. And C is the in the above expression. Above expression means this expression. This expression. C is the covariance matrix. The covariance matrix of n random variables is given by matrix C or Cx is equal to C11, C12 and so on, C1n, C21, C22, C23 and so on, C2n and so on, Cn1, Cn2 and so on, Cnn. So this is the covariance matrix of the random variable, covariance matrix of capital N random variables expression. X minus M transpose is the transpose of the matrix X minus M. So this is the matrix X minus M, and X minus M transpose is interchanging rows with columns and columns with rows. And determinant C, matrix determinant of Cx is equal to matrix C whole to the power of minus 1 is the inverse of matrix C, inverse of matrix C. So we know that the definition of the covariance matrix, and xi and xj are the two random variables. For I is equal to j is equal to 1, 2, 3 and so on, capital N. So the elements of the xi and xj are the elements. The elements of the covariance matrix is given by C suffix ij or covariance of xi comma xj is equal expectation of xi minus xi bar into xj minus xj bar, where xi bar is the mean value of the random variable xi and xj bar is the mean value of the random variable xj. In this equation, substitute I is equal to j, we get the covariance of xi comma xj is the variance of the random variable xi, that is C suffix ij is equal to sigma xi square. Sigma xi square is the variance of the random variable xi. So that is expectation of xi minus mi whole square. If I is equal to j. So if I not equal to j, or if I not equal to j mean the expression is the covariance of the random variable xi comma xj. Cij is the covariance of the random variable xi xj. That is expectation of xi minus xi bar into xj minus xj bar, and these two are the important condition, keep in mind. So now here for example consider two random variables, and what is the previous expression? That expression is the I explained in the previous one. That one is n random variables giant probability density function, and n random variables matrix X minus M, and n random variables covariance of the matrix expression. In that n random variables, for example, here I am considering two random variables. Capital X1 and capital X2 are the two random variables. The joint probability density function of the two random variables is fx1 x2 of x1 comma x2. Okay. So two random variables mean capital N is equal to 2. In the above expression substitute capital N is equal to 2. We get the matrix X minus M is equal to x1 minus m1, x2 minus m2. And this is the matrix X minus M for capital N random variables. This is the covariance matrix for capital N random variables. And this is a covariance definition for capital N random variables. If I is equal to j condition and I not equal to j conditions, in that expression substitute n is equal to 2. Substitute n is equal to 2 mean two random variables case. So for two random variables case, the matrix x minus m is x1 minus m1, x2 minus m2, and the matrix cx is c11, c12, c21, c22. Okay, I is equal to j, c1 cij is equal to sigma x1 square. So c11 is sigma x1 square and c22 is sigma x2 square, and I not equal to j, and I not equal to j, cij is equal to cxi xj, that is sigma x1 sigma xi sigma xj. So c12 is cx1 x2 and c21 is cx2 x1 for 2 for n is equal to 2. And we know that the correlation coefficient rho is equal to covariance of x1 comma x2 divided by sigma x1 sigma x2 for the two random variables. So take the cross multiplication, cx1 x2 or simply c1 c2 is equal rho into sigma x1 sigma x2. In the above matrix, substitute cx1 x2 cx2 x1 c12 c21, substitute in this equation RHS set of this matrix, we get the matrix C is equal, the matrix C is equal or Cx is equal sigma x1 square rho sigma x1 sigma x2 rho sigma x1 sigma x2 sigma x2 square. In this equation, take the determinant on both sides. So determinant of matrix Cx is equal to sigma x1 square into sigma x2 square minus rho sigma x1 sigma x2 into rho sigma x1 sigma x2. So take the determinant on both sides and RHS side. This value into this value minus this value into this value. That is sigma x1 square sigma x2 square minus rho into rho square sigma x1 into sigma x1 square sigma x2 into sigma x2 square. So on both the terms on RHS side, sigma x1 square sigma x2 square is the common. So that is sigma x1 square sigma x2 square into 1 minus rho square, and take and find out the adjoint value of the matrix Cx. So the adjoint matrix of Cx is interchanging this value and this value, interchanging, sorry, and the adjoint value is sigma x1 square sigma x2 square into next calculate the adjoint matrix of Cx. So the adjoint matrix of Cx is interchanging sigma x1 square sigma x2 square. So that is sigma x2 square sigma x1 square, and here the interchanging the this c12 and c21 values, and okay, take the negative sign of c12 c21, we get minus rho sigma x1 sigma x2 minus rho sigma x1 sigma x2. That is adjoint matrix of matrix Cx, adjoint matrix of Cx. Next, determine inverse matrix. C inverse is equal to adjoint matrix of Cx divided by determinant of Cx. So dividing adjoint matrix divided by matrix Cx, and what is the determinant C? This is the determinant C, and this is the adjoint matrix. So this adjoint matrix divided by this one. So we get adjoint matrix of Cx divided by determinant of Cx is 1 by 1 minus rho square 1 by sigma x1 square minus rho. And now here what is the term? Adjoint matrix sigma x2 square divided by determinant. And what is the determinant matrix? Sigma x1 square sigma x2 square into 1 by into 1 minus rho square. So numerator and denominator sigma x2 square is the common cancel, and remaining term is 1 divided by sigma x1 square into 1 by into 1 minus rho square. For all the terms, 1 by 1 minus rho square is the common, that is written before matrix. Okay, and the remaining term of this here is 1 by sigma x1 square. And the second term here, and what is the adjoint matrix? Minus rho sigma x1 sigma x2 divided by determinant matrix. And what is the determinant matrix? Sigma x1 square, sigma x2 square into 1 minus rho square. So 1 by 1 minus rho square is written here. And second term numerator and denominator, 1 sigma x1, 1 sigma x2 is the cancel, and the remaining term is minus rho divided by sigma x1, sigma x2. And similarly here also minus rho by sigma x1, sigma x2. Here is 1 by sigma x2 square. So that is the inverse matrix Cx inverse. So now take x minus m transpose into Cx inverse into x minus m. What is that one? And what is the definition of the n random variables joint density function? And this is the definition of the n random variables probability density function definition. Now consider x minus m transpose into C inverse x minus m. First calculate this term and substitute this term into two random variables giant probability density function expression. Finally we get n random variables giant probability density function expression. Okay. Now consider x minus m transpose Cx inverse into x minus m. And what is the matrix x minus m? The matrix x minus 1 is 2 rows and 1 columns, x1 minus m1, x2 minus m2, and x minus m transpose is 1 row 2 rows, that is x1 minus m1, x2 minus m2 into Cx inverse is, this is the Cx inverse 1 by 1 minus rho square into 1 by sigma x1 square minus rho by sigma x1 sigma x2 minus rho by sigma x1 sigma x2 1 by sigma x2 square into x minus m matrix is x1 minus m1 x2 minus m2, and multiplying using matrix multiplication, multiplying RHS term we get. So first multiplying these two terms, so the RHS term is also arranged as 1 by 1 minus rho square into remaining terms. So first multiplying these two terms. So this matrix order is 2 by 2. This matrix is order is 2 by 1. Multiplying these two matrices, we get 2 by 1 order matrix. So first multiplying. Okay, first multiplying this matrix into this matrix. This matrix order is 1 by 2. This matrix order is 2 by 1. The resultant matrix order is 1 by 2. Okay, x1 minus m1 into 1 by sigma x1 square, x1 minus m1 into minus rho by sigma x1 sigma x2, so that is, and x2 minus m2 into minus rho by sigma x1 sigma x2, x2 minus m2 by sigma x2 square, that is multiplying these two matrices we have x1 minus m1 by sigma x1 square minus rho x2 m2 by sigma x1 sigma x2 minus rho x1 minus m1 by sigma x1 sigma x2 plus x2 minus m2 by sigma x2 square into x1 minus m1 x2 minus m2. Now multiplying these two matrices, this matrix order is 1 by 2, this matrix order is 2 by 1. So multiplying 1 by 2 and 2 by 1 matrices, the resultant matrix order is 1 by 1. Okay, that is this value into this plus this value into this. So therefore 1 by 1 minus rho square into 1 RHS term 1 by 1 minus rho square into x1 minus m1, okay, First I will explain here, after that showing. So x1 minus m1 into this term, x1 minus m1 whole square by sigma x1 square minus rho x1 minus m1 into x2 minus m2 by sigma x1 sigma x2 plus into minus rho x1 minus m2 x2 minus m2 by sigma x1 sigma x2 plus x2 minus m2 whole square by sigma x2 square. So that is one by one order matrix. So that is this one. And simplifying the RHS term, 1 by 1 minus rho square is equal x1 minus m1 square by sigma x1 square okay minus rho x1 minus m1 x2 minus m2 by sigma x1 sigma x2. This term and this term is minus 2 rho x1 minus m1 x2 minus m2 by sigma x1 sigma x2 plus x2 minus m2 whole square by sigma x2 square. And what is the general expression of the joint probability density function f of x1 comma x2 and so on, x1 comma x2 and so on xn is equal to general expression. In that now here we are considering two random variables, capital N is equal to 2. In that general expression, substitute capital N is equal to 2, we get 1 divided by 2 pi whole to the power of n by 2 general expression. Now here capital N is equal to 2 by 2. So into determinant of Cx whole to the power of 1 by 2 exponential of x minus m transpose into C inverse x minus m. So this value already calculated. And what is that one? That value, this one. X minus m transpose C inverse x minus m. That value is this one. And substitute this value into here, we get the joint density function fx1 x2 of x1 comma x2 is equal 1 divided by 2 pi. And what is the determinant of Cx value? Determinant of Cx value is already calculated. That value is sigma x1 square sigma x2 square into 1 minus rho square whole to the power of 1 by 2 exponential of minus 1 by 2. This term is 1 by 1 minus rho square into x1 minus m1 whole square by sigma x1 square minus 2 rho x1 minus m1 x2 minus m2 divided by sigma x1 sigma x2 plus x2 minus m2 whole square by sigma x2. And initially the jointly Gaussian random variable concept, starting I explained two random variables definition. And what is the two random variables joint density function? This is the two random variables joint density function expression. So therefore 1 by 2 pi, simplifying the RHS term of the above equation, we get 1 by 2 pi sigma x1 sigma x2 into square root of 1 minus rho square exponential of minus 1 by 2 1 minus rho square x1 minus m1 whole square by sigma x1 square minus 2 rho x1 minus m1 x2 minus m2 by sigma x1 sigma x2 plus x2 minus m2 whole square by sigma x2 square. First, the random variables x1 and x2 are said to be jointly Gaussian random variables if their joint density function as shown in above expression. This is the joint probability density function expression. This indicate in the above expression, substitute correlation coefficient rho is equal to 0. So correlation coefficient rho is equal to 0 means two random variables x1 and x2 are said to be uncorrelated random variables or independent random variables. If the random variables x1 and x2 are the uncorrelated, then the correlation coefficient rho is equal to 0. Substitute rho is equal to 0 into the above expression, we get the joint density function expression is f x1 x2 of x1 comma x2 is equal 1 by 2 pi above expression substitute rho is equal to 0. We get the remaining RHS term is 1 by 2 pi exponential of minus 1 by 2 into x1 minus m1 whole square by sigma x1 square plus x2 minus m2 whole square by sigma x2. So the RHS term of this equation is also written as 1 by square root of 2 pi sigma x1 square e power minus of x1 minus m1 whole square by 2 sigma x1 square into 1 by square root of 2 pi sigma x2 square e power minus of x2 minus m2 whole square by 2 sigma x2 square. So multiplying this term and this term, we get 1 by 2 pi, 1 by 2 pi. Okay, and this is the exponential term. E power of this term is written as e power of this term into e power of this term. E power a plus b is written as e power a into e power b. E power a into e power b. So the RHS term can also be arranged as this one. So the first term is the Gaussian density function definition of the random variable x1, and the second term is the uh, density function of the Gaussian density function of the random variable x2. So that is fx1 of x1 into fx2 of x2. The first term is Gaussian density function of the random variable x1, and the second term is Gaussian density function of the random variable x2. So this means that if rho is equal to 0, the joint density function is equal to product of their individual density functions. That is fx1 x2 of x1 comma x2 is equal to fx1 of x1 into fx2 of x2. So this indicates the random variables x1 and x2 are Gaussian and independent. Gaussian random variables and independent. Thus, two jointly Gaussian random variables that are uncorrelated are also independent, irrespective of the value of the rho. The marginal densities of the above two random variables are Gaussian. But the converge may not be true. That is, if the random variables are individually Gaussian, then the jointly they may not be Gaussian. This is the concept of jointly Gaussian random variables for the two random variable case and for n random variables case.